Hello. Okay, so this is the last video that I'm going to record in this series. Hopefully this will help you with that assignment if you need help. Okay, so this graph here is basically the same thing as this graph here that I did in the other video. It's the same thing. We're just taking log base 2 of x. But what I did instead is I just graphed this over certain whole number values, so you can kind of see whole numbers instead of decimals, and you'll see where I'm getting at with this soon. But anyway, so we have this one, x equals 4, so this means log base 2 of 4 is going to be 2. If we do this multiple times, this means 2 plus 2 plus 2 is going to equal 6. So log base 2 of 4 plus that is going to be log base 2 of 64. Now, the way that works is, well, you can think of it this way too. If you had to, if you add, remember, you multiply each of these numbers. 4 times 4 is 16. 16 times 4 is 64. So in other words, this whole expression is log base 2 of 4 cubed. Log base 2 of 4 cubed. Okay? And we have another example. So let's say we have, let's say when we add these here, recall that this is the same thing as combining like terms. Like what if this was x plus x plus x equals 3x, right? So just this here. So if this is x and this is x, x plus x plus x equals 3x. So this expression is the same as this. So what this implies is that this expression, log base 2 of 4 cubed, is the same thing as 3 times log base 2 of 4, which is described right there. Okay? You can use the same idea for this one. Use the same idea for this here. This is the same thing. You have 2 times 2 times 2 times 2 times 2. So this is the same thing as log base 2 times 2 raised to the 5. Okay? Okay, so yeah, if you guys are wondering where that's coming from, so up here, log base 2 of 2 is 1. So basically what we're doing is just 1 plus 1 plus 1 plus 1 plus 1. And that should equal log base 2 of 32. So that should be 5. Okay. What you're going to realize then is if you had to do the same thing, combine like terms here. If this was x plus x plus x plus x plus x, that equals 5 times x. Right? So what this is implying is this expression is the same thing as that expression. Okay? So that's another way that you could do that. Okay? So if you have noticed, if you kind of see a pattern here, the pattern that I'm trying to show is that basically this cube can be brought down for logarithms. And this 5 can be brought down, it's the same thing as multiplying for logarithms. And you can see that in this example here too. I'll let you try to figure it out. But in general, the power property says that if you have any logarithm, if raised to exponent, that exponent can be thrown in the front. Okay? So what I'm going to show you is an example. Okay, so what we want to do is we want to rewrite each logarithm using the power property. Okay, so what I see here is that this is log base 4 x cubed. So basically this is just going to come right down here. So this is the same thing as 3 log base 4 of x. That's it. Okay, so this exponent gets dropped down here This is 8 times the log of 15, log base 15 of x. Okay. For this one, the 14 comes down here. This is 14 log base 7 of x. For this one, the x will come down here. This is x times log base 2 of 3. This one, x, gets moved down there. So this is x times log base 12 of 8. Same thing for this one. This gets dropped down here. X times log base 6 of 8. Okay? Alright. So, hopefully that helps with this part. Okay? Not terribly hard if you see a pattern. Okay, so now let's go back to quarantine assignment number 1. Okay, so quarantine assignment number 1, if you guys did it, so annual sales for a clothing store, you start with 270,000, and it's the sales will increase by 7% per year. And how many years will it take for the store to reach a total of $330,000 and $761? Wait, $330,000 and $761. Okay, so what you would do for this, if you guys did that, recall that this is the exponential growth formula. So f of t is your final amount, a is your initial amount, r is your percent, t, you're trying to find out how many years it takes for the store to reach that amount. Okay, so what we did in the other lesson, right? So what we did was we had this, and then I had you graph it, graph the left hand side and the right hand side, and that's how we could get around solving this without understanding logarithms. But now that I'm teaching logarithms, we can actually go ahead and solve this. Okay, so what I see here is, if I were to solve this, I can divide both sides by 270,000. So if I divide both sides by 270,000 here, what I am left with is, I'm going to do that really fast, 330,761 divided by 270,000. So this is going to be about 1.225, and then equals 1.07 raised to the t. Okay, so now what we're going to do is we're going to take, so if some of you see this already, it's in that form where we could express this as a logarithm. This is our base, this is our answer, and this is our, this is our base, this is our exponent, and this is our answer. Right? Now, what I'm going to help you out with is, you can take the log of both sides. So log of 1.225 equals log of 1.07 raised to the t. So you're taking the log of both sides. Now, as you see, if I just cover this here, I cover this here, these problems that I showed you up here, you can apply that to this here. So the t gets dropped down. So the t is going to get dropped down. So this is log of 1.225 equals t times log of 1.07. Now, whenever you see these logarithms, just remember, logarithm is an exponent. So it's still a number. So in order to solve for t here, I can divide both sides by log of 1.07, and I can solve for t. Okay, so I'm going to do that real fast, showing you that using Desmos. So if I were to do that, log of 1.225 divided by log of 1.07. So if you see here, so log of 1.225 divided by log of 1.07. So my output is gonna, so t is gonna be about 2.999 years. So this means t is approximately 3 years. And this is how we would go about solving it if we if we didn't want to graph it using technology, if that makes sense. Okay, so that's how you would do that. That's what I want to show you there. Those are all the steps. Okay, so let me show you another example. So the other example that we went over was the coronavirus example. So the coronavirus example. So if you have 300,000 cases in the world, this was a while ago. It's much more than that now. But if we all social distance, then hopefully we see a decrease per month. But who knows if that really happens. But let's say if this was true, how many months would it take to get 250 active cases instead of the 300,000 at that time? So 300,000 is our initial amount. That's A. 250 is what we're trying to get to, so that's our final value. And then you just plug into the exponential decay formula. So 1 minus and then 45%. So this is what we start with. So if you had to calculate this by hand, divide both sides by 300,000. I'm going to go ahead and calculate that. 250 divided by 300,000. So I got 0.00083 equals 0.55 raised to t. Okay, so if you guys notice the pattern in the other one, so what we did was we took the log of both sides. Log of 0.00083 equals log of 0.55 raised to t. Okay, so just like in the other problem, so what we did was that if you have an exponent in front of for a logarithm, you can put it right in the front and treat it as multiplication. So this t gets thrown in the front. So this is log of 0.00083 equals t times log of 0.55. So we can solve for t if we divide both sides by log of 0.55. So in this case, we're left with t equals this here. So I'm going to go ahead and calculate that for you. Log of 0.00083 and divided by log of 0.55. Okay. And as you see here, that's our result. So we have about 11.86. That's what we got. So this would be 11.86, so approximately 11.86 months. That's how long it would take for hopefully the coronavirus to disappear based on these parameters. So 11.86 months. Yeah. And that is what I have there. Okay. So I'm going to show you 2 more examples and then that will be it. Okay. So same idea here. So let's say you have a different example. So this was the continuously compounded formula that some of you may have done, right? So same thing. So use this formula for continuously compounded interest. So P is our initial value. That's 6,750. Our rate, you convert this to a decimal. And then you're trying to find the value of investment when it reaches $15,000. So once you plug in these parameters, then what we need to do is we need to solve for t somehow. So in order to solve for t, what I see is we can divide both sides by 6,750. So if I do that, so 15,000 divided by 6,750. If I do that real fast here, so you guys can see that. So that's 2.22222. Okay, so 2.222 equals E raised to 0.0623 raised to T. So same idea. What you see here is, in order to try and solve this, you take the log of both sides. So log E 0.0623 raised to T. So now this whole part here is considered exponent. When you have a log, you can throw that whole thing in the front. So this is going to be log of 2.22 equals 0.0623 T times log of E. Okay, so what I see here is I can divide both sides by log of E. Log, so if you guys remember what E is just a constant. So this disappears. So now I can just type in log of 2.222 divided by log of E. So I can show that real fast right there. It's going to be 0.7985 or so. So this is going to be 0.7985 equals 0.0623 times T. Last, what we need to do is we need to divide both sides by 0.0623. 0.0623, which means our time is going to be 0.7985 divided by 0.0623. Okay, so that's what we're left with. So if you see that there, what that means is the amount of time it reaches for that investment, the 6,750 investment to reach $15,000, is going to be about 12.82 years. So that is going to be a while. Okay, so yeah, that is basically how you would go about doing those problems. Now if you want, you can, if you need help on the last one, just ask me if you need help on the last one. One thing I want to show you though, so as we were trying to solve these, you can also connect it to what I was showing you earlier with logarithms, right? So let's say, I'm just going to turn this around, sorry. So earlier I showed you that 330761 equals 27000 times 1.07 raised to the T, right? So what we did was we simplified this down, and when we simplified this, we got 1.225 raised to the 1.07 T. So if we were to work backwards, so remember that log, in order to write a logarithm, we need to know our base. Our base is 1.07. Our answer is going to be 1.225, and our exponent is what we are trying to solve for. We said a logarithm is an exponent. So this is T, which equals log of 1.225 divided by log of 1.07. And that is basically the change of base formula that I showed you from the first video. Yeah. So that is another way that you could go about doing it. So this might take a little while to get from this step to this step, but I'll try to emphasize that in a later video. But I just wanted to show you that if you guys didn't want to do all those other intermediate steps. But it's good to see those intermediate steps. Okay, hopefully that helps, and I will see you later. Bye.